Okay, good morning. Today we'll be having two lectures, one on evolution of NLP and the next one is on introduction to word embeddings. Both of them are going to again set the base for the course, and we'll be seeing kind of a story thing like how we saw in the introduction to NLP part in this evolution lecture, and we'll have some math in the next lecture. I'm trying to keep like one slide has math and the other is a bit more streamlined. So let's get started. So we'll be saying that natural language processing has been around right from the medieval ages, and people have tried to make systems compute language, and it need not involve a computer, as we saw in the last class also. Then I'll not be discussing what the Turing test is, but I'm just putting it there because it's also a language processing task. And we'll be seeing so on and so forth. I think it makes no sense to list them here without discussing. In the end, I'll be spending some time on the common evaluation metrics, and also I added some discussion on bias versus variance. And you might have seen the question that was given yesterday. I was curious what is the current understanding of the topic. And yeah, let's get started. So the first thing is people were trying to build a machine that could do translation. Machine translation is one of the common natural language processing tasks that people wanted to automate so that we could understand. And definitely living in Germany, I can say Google Translate is the one app I count on apart from Google Maps to get around. And then this was done in the late part of the 1700s, 1800s, that kind of a thing. So medieval means I don't mean the early part, the late part. So here we have people like Leibniz who are building machines, and this caught the public attention and people were making fun of it also. So that shows how technology was always kind of seen cautiously, the way even today AI is seen, like whether we should do it or not, and so forth. So in the 1900s, a Russian scientist came up with translating using this language called Esperanto. You might have heard of it. It's an intermediate language for European languages. So you can convert or translate from European or Latin-based language to Esperanto, and then to any other language, say German or something. There's a very interesting history with Esperanto as well. You can read it later. And then in 1950, we had Alan Turing's famous Turing test paper that sparked off so much debate and has become the iconic symbol of natural language processing. In 1957, Chomsky claimed, like we saw in the last class, as kind of universal grammar. So it is like he argued that it is inherent to how people think and what the structures they have in their head, that it is universal, and all our brains are tuned such that the verb phrases or prepositions, or we have some defining characteristic that helps us understand any language. So what is that universal grammar? It's not just a grammar for each language, but he tried to come up with a way to extract a universal grammar that will apply to all languages. Now, in between, in 1954, there was a Georgetown IBM experiment. What was this? So they converted 60 sentences from Russian to English and showed the first success of machine translation. And you can see the computers are still huge. It's quite difficult to do more than 60. Now, if somebody were to give a data set of size 60, it's unheard of, right? So this experiment attracted a lot of funding because there were actual results you could see. Till now, people were seeing theoretical concepts or proposals, but this was something that actually did the translation. But what happened was the researchers got carried away and publicly said that in 10 years we would solve machine translation, and that it so that sort of led to a loss in trust, and people stopped funding general machine translation or NLP tasks, saying that this was promised a lot, but we are not seeing any results. And I'm not sure if this sentence is related with this experiment, but there's a sentence which is like, which is from the Bible, which goes, "The spirit is willing, but the flesh is weak." Which means when you set your mind to do something, you have the will, but you go back into your old habits. But it was translated into Russian and back to English like, "The whiskey is strong, but the meat is rotten." So these kind of problems in machine learning, and you might have done this in Google Translate, just translate to some random language and then translate it back to English, and it used to give very funny results. Maybe it has improved now. So that was the state in like 1950s, that sort of a thing. Then Roger Schank said, "We are looking at language wrongly by focusing too much on the grammar. We need to focus on the meaning. Instead of focusing whether it is a verb or a noun or things like that, we need to understand what these words represent, right?" So he came up with a theory that all the sentences in a language fit into very few semantic roles. For example, so this theory was called Conceptual Dependency Theory, or CD theory. So given a sentence like this, "I gave the man a book," then what that would imply is that this is a part of a structure or a category called A-trans, which stands for abstract transfer. So in A-trans, you don't you transfer a book, and so because it's like, "I give the man," which direction you're giving. So it's like from I to man, that sort of, and these are relations. I forgot what each of the relations stands for. I think O is like object or something. It's a huge dictionary, basically telling what are the limited number of roles, limited number of concepts, and so on. So once we have that, we can convert each of these sentences to this particular form. Now, this kind of approach where you convert the natural language to an intermediate form is what is called as semantic parsing. It has become its own field now. But he was one of the early users of this idea, and it was very popular. He had, I think, for around 20 years, he was using CD theory, and he built a lot of he had a lot of PhD students working on that and improved upon it. So he basically came up with rules to convert the sentences to this intermediate representation, and then he started working on extracting even more information. For example, he said, not only do we have language and semantics at the sentence level, but even an entire paragraph or a discourse has a lot of information we can exploit. So he said that we need to set up expectations. For example, when you visit a restaurant, you know that you're expected to sit in a place, you're expected to take the menu card or tell what you want to eat, and so on. So this kind of, if I had a script, so this was how CD theory was incorporated into a script to say that if it is a restaurant, then I will have a lot of ideas that this is the procedure to follow, and I will look for words or sentences that fill these ideas. So what happened is, even if you write the text in a jumbled fashion, the script will kind of order them. Now we come to something a bit interesting. So in MIT in 1968, they came up with this program where the user, the person, types only text, but it gets translated to something visual. So there is a blocks world created by the programmer, and there is a configuration of blocks specified every time differently. And then there are a set of instructions, and the computer does it and also represents it in language. So it goes like pick up a big red block, okay, grasp the pyramid. I don't understand which pyramid. So you can see it's interesting. Once again, like the translation part, you can actually see the output. And there are two big processes. It is not just language, it is also being connected to a task. So I've not spoken much about planning, but planning is another part of AI, and it's quite important in robotics and other fields, which will not be discussing. But planning generally involves knowing, okay, I have a start configuration. What is my final configuration? What are the allowed actions? What are the preconditions? What are the effects? And I go from one state to the other till I reach the goal condition. So, for example, pick a big red block would have conditions like there should not be anything else above it, and so on. So, apart from all of this, it also does question answering, like what does the box contain? The blue pyramid or the blue block? So again, it's quite interesting, and it came out in like 60s. So these are all rule-based systems which, so if I gave language input, it would play around with that, pick up words, pick up key phrases, and write programs. So can somebody sort of summarize, of all the systems we saw, what is the common theme? What can you make out from that? Can you give some idea why this approach stopped being popular? And do you think industries are still using these kind of rule-based systems? Can someone give it a try? Or maybe we can just go with, do you think industry still uses? I think the common theme is quite evident that we use rules throughout, and this approach died out basically because it's very domain intensive. A domain expert has to set the rules, and it might not generalize in future. But do you think industries still use this? That is the interesting part, I guess. Yes, Ayush?
I don't think so, because they're
Mm.
using deep learning models nowadays, from what I've
Oh,
seen.
mhm. Great. So, yes, I think um, by in industry, it is quite common to see only deep learning. But the industries that do use these kind of symbolic measures are, for example, we had a project in Ford, in the automobile company. So what happens there is, they don't want to take a chance that machine learning or deep learning has in the sense. All these approaches have a precision of say 99.99%. Even that point, not 1%, can lead to a big loss. In these kind of situations, even now, industries do use symbolic error methods when the procedure is very certain. Like in a car industry or any factory for that matter, you already have a very established procedure. So you have possibly for diagnostic a lot of sensors, and you're trying to identify the problems or the next step and things like that. So it's not out of fashion per se, but definitely for research and for future works, like it's going in the other direction. But we do now and again pick up things from the symbolic era because it involves a lot of knowledge For example, I spoke about memory. In the symbolic era, there were a lot of structures that used memory, and the kind of research that happened here in the symbolic era also led to development of OOP concepts and the programming languages we saw. So we do now and again go back and pick from the symbolic era. It's not completely wiped out. But yes, as you said correctly, we are all moving towards the machine learning and statistical era. And as we saw in the last class, we have increased storage capacity, processing capacity. So it led to the rise in statistical methods. And you might have seen in your other course SVMs and many other methods. And it also led to interdisciplinary research. So we could depend on our biology research to develop neural models and so on. And the fundamental thing which drove that was, as we saw last time, that language could not be captured by rules. So how do we get over this? So we started using a lot of annotated corpora in the natural language processing domain. What do I mean by annotated corpora? It is just, so corpora is just basically plural of corpus, where corpus refers to a body of text, and annotated means you label them basically. And for example, pause tagging, part of speech tagging. Now, the question is, are we using only labeled corpora? Unlabeled text corpora is one of the big game changers of natural language processing, because we have so much of it, like Wikipedia or tweets, or so there's just so much data and text on the internet. We also call it unstructured data. And one of the early corpus that was used was the brown corpus. And there's so many used now, just starting with a bit of history. This also interestingly led to this semi-supervised learning, because we have a lot of text and we might be able to label only a small part of it. So how do I use that information and cascade it down to the unlabeled part? So with this framework, most tasks in NLP started having corpora, which is just like having a data set, and we can either use it as a tool for a data set, or this itself can be the data set. I'll be showing a few examples. Let me give an example of few tools that were used. So one is the pen tree bank, which was developed at the university. What it did was, there's a huge corpus, and every sentence in the corpus is represented with its part of speech and the tree. This is a constituency parse tree, which says, okay, this is the sentence, this is the noun phrase, this is the verb phrase, and so on and so forth. So these are the part of speech tags that are allowed in the pen tree bank, and this became a tool to perform part of speech tagging. So the interesting thing is, if you give a sentence, there is no one parse of the tree. There are many parses, and depending on the context, one of it is valid. So we saw disambiguation also in the last class. And by training this data set, we get much better parse trees. So this was an annotated effort. A lot of human annotation was involved, and then they were seeing how much the human annotators are agreeing, and so on and so forth. Next, we have a very interesting dictionary called WordNet. So this is not a corpus as such, but it basically, going back to Roger Shang's theory, tried to impart semantics to words. So to say, for example, that carrot and radish are parts of the class of root, and that is a class of natural object. So it developed a kind of inheritance. So this is a relation. Like that, there were other relations, and this is for nouns. There were similar hierarchies for verbs and so on. And all of the tree culminated in the root called entity. So what this did was it captured a lot of information. For example, synonymy, many words that have the same meaning, or hypernymy, the same word having multiple meanings. They are differentiated because they will be present in different parts of the tree. Now, what this story implied was that machine learning started focusing on understanding graph theory and graphs. So, for example, if I have a feature that says good is a positive sentiment, I can say that all the words that are close to it in this inheritance tree are also part of this word good. It becomes a concept good. So there are a lot of measures like the lowest common ancestor and so on to show whether two words in the word tree are related. So the pros and cons are very simple. The pros are that, yes, it developed a lot of statistical methods and it brought in a lot of revolution. The con, as you can imagine, is you have a lot of annotation. Humans have to sit and read through tons of text and decide whether it is this particular part of speech and so on and so forth. But lucky for us, most of these corpora based annotation is already done, that we can just build upon that. But you can imagine for some very specific domain, you'd still have to sit and do it from scratch. So with this scenario, neural embeddings became very popular in 2014. We'll be seeing in the next lecture that embeddings, sorry, that's a spelling mistake, I'll correct that. Embeddings existed before. It's not that suddenly when neural networks came alone that, embeddings were there. But with the large network and data, we were able to obtain a lot of nice features in these neural embeddings, as we will be seeing. So now we'll spend some time on the evaluation measures for NLP algorithms, precision, recall, and so on. We'll see. So first we'll look at classification metrics. So in classification, let's say between two classes, a positive class and a negative class, we have 4 kinds of data: the true positive, true negative, and false negative. What do I mean by this? By true positive, I mean that the algorithm predicted positive, the data was also positive. By false positive, I mean algorithm says it is positive, but the data is negative. So the opposite words like false positive and false negative, they are both the mistakes that the algorithm has made. True positive and true negative are what we desire. So using this idea, the straightforward measure is accuracy, where accuracy is correct classification by total, or the true positive plus true negative by total. But do we want to know more about our algorithm? Is this sort of averaging enough? That is the thing that led to the next classification metrics. So let's take an example. If I have total 50 positive, 50 negative, and true positive 40, true negative is 30, then I know accuracy is 70%. And this is what any straightforward approach would be. Now, what if I wanted to measure how good it classifies one particular class? Okay, so then I would say, what is true positive? So here, I will change this from the next slide. This is 60 and 40. Okay. So I want to say true positive out of all the positive that are there. So this is 40 out of 50. So that's 80%. And in the negative class, it's only 30. So it comes down to 60%. Okay. I'm sorry about that. There are a few mistakes here. So here I wanted to say it is recall, not precision. Yeah. Okay. So in precision, we have true positive out of all. So what I'm trying to say, forget the formula for the moment. What I'm trying to say is I have classified so many things as positive. Out of that, how many are positive? So I have predicted 50 are positive. So out of that, 40 was positive. So it's 80%. Now in the negative class, I have predicted again 50 are negative. How many are negative? 30. So it's 60%. So from this, I can judge that my algorithm is predicting the positive class better than the negative class. And usually, because the data itself has 60-40, whichever is the majority class, the algorithm would be better. Now in recall, what we do is, we want to know how much has been retrieved, which is the what to say, like how relevant thing. So if totally I am having some number of positive, how much has been retrieved? So as you can see, the numerator it's the same. It's only the denominator that is changing. What does this mean? We are measuring different kind of things, and you actually want to look at both. You'll want to look whether whatever was positive was done positively, and from what you have received as positive, what you have got. So we want to combine both, but we can't take the average because as you can see, the denominator is different. So we take the harmonic mean, which is the average of the reciprocals. So now, what do we do in retrieval? Retrieval, we use the same metrics, but the semantics is changed. We say that it's retrieval versus relevance. So here, precision becomes number of relevant documents that were retrieved by total retrieved, and recall becomes number of relevant retrieved by total relevant. Once again, the denominator is what is different. So again, F1 score is measured, which is the combination. That is the harmonic mean. Now we'll be looking at similarity matrix. Why this is important is we will be dealing for majority of our course vectorial representations, and when we have two vectors, how do we compare them? Do we say they are similar or very different? So a common measure is to use the cosine similarity. So you have two vectors of the same length, and then you normalize them, take the dot product, and this gives us a scalar, and this scalar is between 0 and 1. So it's very useful for measurements, and we can describe whether vectors are similar or not. Next, we have the Jaccard similarity. Jaccard similarity is not for vectors, but for two sets of objects. So it's a very simple measure. I'm just saying in the sets of objects, what is the intersection divided by the union. So it's basically this part by the sum of these two. And that is how similar the sets A and B are. You can imagine if the intersection is 0, then we say it's not at all similar. And if the intersection is the union, then it's completely similar. They're one and the same, basically. And that is an interesting measure, and it's one of the easiest to code, as you can imagine. Now we have a set of metrics for generation. So we saw last class what is generation. It's like translation or summarization and so on. These kind of tasks are hard to evaluate. How do you say it's a good translation or good summarization? So the usual method is to compare it with a human annotated reference. So I have a human translation and I will measure how good it is based on the candidate or the machine translation. One of the most popular scores is the BLUE score. It stands for bilingual language something understudy. It's an acronym that came that it sounds like blue. And given a sentence and many candidate sentences, we want to measure how many words in the candidate are occurring in the reference sentences. And so that is given by this formula. You'll be going into a little bit of detail. So quickly, I will touch about what is n-gram. So by n-gram, I mean the combinations, n combinations. So unigram, one-word combinations, bigram is two-word combinations, and trigram is three-word combinations. We don't go more than this because it's not often useful. And but theoretically, any n is possible. For example, if you have a sentence, the cat ran, the set of unigrams would be the, comma, cat, comma, ran. The bigram would be combinations of two, the cat and cat ran. Also here it's important that it's not cyclic. We don't like finish and come back to this. It's set of things in the sentence, basically. The cat ran. And this is, here we have a single sentence. You might even have multiple sentences. It's still taken in that order. It's not like we have converted it into a set of words and we are saying all two-word combinations. It's not that. It involves a sort of sentence structure and ordering, and we can gain a lot of information from bigrams and trigrams. And the trigram would be the cat ran. So in normal precision, what we would do is the number present in the reference by the total in the candidate. But here in blue score, what we do is we set a limit. We say that it should be only up till the largest frequency in the reference. What do I mean by this? So they noticed a problem when you use precision. If you have a candidate like the, and the actual correct translation was the cat ran. So this would say the precision is 100% because the word the occurs in the reference and all the three words occur in the reference. So it's 100%. Clearly you can see something is wrong. So what they do is every word is allowed to repeat only the number of times it's there in the candidate. So the can occur only one time. So once a single the is counted, the other two scores become 0. So here the blue score becomes 1/3. And generalizing it a little bit, we'll be doing this with n-grams instead of single words. And this is summed over all the candidates. And this is your final blue score. Next, you have a variation called the Nist Metric. What this does is it weights by the frequency of bigram. What do I mean by that? So if a bigram such as on the phrase on the is so frequent in all data sets, and you have one bigram on the and another bigram saying interesting book, then the bigram interesting book will have more weight because it's more rare and more important for your translation. And we will be seeing this idea, which is which are the important words or the important bigram, trigram, when we look at attention in deep learning later in the course. So this kind of weighting measure improved the blue score a lot. Next, finally, we have a Rouge metric. So what this does is, till now, we were looking at precision. Rouge metric flips it and looks at it from the perspective of recall. So there it says, I don't care how many times I have retrieved a word, which is what all the precision-based methods were doing. As long as there is a word in the reference candidate, I want to see how much it is happening in the algorithm candidate. So the first one is just overlap we are having between the system and the reference summaries. Rouge was used more for summaries than for translation. So we saw two sets of metrics, one based on precision and one based on recall. Usually there is a precision recall trade-off. We cannot maximize on both without losing something of the other. So we usually try and go to a moderate precision, moderate recall kind of place. And that is what deep learning excels in. And we will be seeing that later. Now we come to ranking metrics. So by ranking, I mean things like our Google search, where it just, spits out so many search results so fast. How does it rank them? What is relevant to you? You might have seen it involves a lot of personalization and so on. But in a very basic sense, where you just have a set of documents and you're retrieving, some of the basic metrics are mean reciprocal rank and mean average precision. What do I mean by this? Say that my most relevant answer is at rank 3, then I just take the reciprocal and say, okay, my score is 1/3. What does this mean? If my most relevant answer is at rank 1, my rank will be 1, because reciprocal of 1 is 1, and it's 100%. If it's at rank 2, then it would be half or 50%, and so on. And average precision, just as it says, it's the mean of the average precision. So what does this mean? So in retrieval, I will get a set of ranks or a set of candidates, and the precision of each candidate, I will average it, and this I will take the mean over all the candidates. So that's why there is mean and average, because one set itself I can measure an average, then I'll be taking mean over all of that. Just to differentiate between the two for loops we are having, we say mean first and then average. Then we have something interesting known as annotated agreement. So what happens is, as we see in Corpora, a lot of annotation is required. And when we have two data sets, we try and figure out whether they have annotated with agreement. So one way we measure this is the Kappa Statistic, which is basically telling what is the probability of agreement and the expectation. So it's, in a nutshell, what it's trying to do is, what is the actual agreement, which is basically this column. So if I have two annotators A and B, and the agreement is basically 54 plus 18 plus 72. What is the agreement you expect? It's basically how much I have said is positive and this person has said positive, which is basically you want these scores to agree: 85, 67 and 72, 98 and 93. Now, because 85 is an 100% agreement, you say that the class POS or positive has been annotated perfectly. As in this, we don't know if it's annotated perfectly, but there's perfect annotated agreement between the two of them. So that is the intuition behind both. So now I have an interesting thought. So you might have seen natural language processing involves tokenization, which is basically converting the sentences into words. It may involve lemmatization or stemming. The difference is lemmatization converts the word into a root. Say if I have a word like running, it converts it into the word run. Stemming also does that, but the difference is in lemma, the root word has to make sense. For example, the word argument, my lemma would be argue, A-R-G-U-E. But in my stemming procedure, it will just be A-R-G-U, because I can have multiple words after ARGU that can be derived from this word argument and form further forms. So lemmatization and stemming are parts of analysis. And then we have sentence detection. Now, if you do NLP in any task, any framework like NLTK or Spacey or anything, you will just get the set of sentences, lemma, tokens, might not even use lemma, and move forward. But did you know sentence boundary detection is it in itself a popular NLP task? Why do you think this is difficult? Can someone give an idea why sentence detection is difficult?
I mean, is
Uh,
it
yeah.
semantically difficult? Like not grammatically, like you can see the like period, like end of sentence, but
Mm-hmm.
semantically, like if you want to convey one thought, like that's what a sentence should be, but it can be spread over multiple like grammatical sentences.
No, no, I'm talking only about syntax. Think why the period or full stop is a bit problematic. Where else do we use period or full stop? So you headed in the right direction. What happens is we use, unfortunately, we use the period itself quite often in decimals, and we use colon, semicolon. When you read text, there's a lot of different um, punctuations and things which make it difficult. And there is a famous corpus for this called Wall Street Journal corpus, because you can imagine in such a corpus, we'd have a lot of numbers with decimals and so on and so forth. That it's a solved problem almost with all the statistics and label data, but um, it's not a trivial problem. As even I thought when I started the course, I would just look at where the full stop is and go on. But when you see that Wall Street Journal, it is crazy. It's very hard to find out where the sentence is ending for a computer. Like, we will do it automatically, but yeah, I thought this was something interesting. So I'll spend some time. We have around 15 minutes, maybe the next 5 minutes, on bias versus variance. So I wanted to focus on this because all the algorithms we'll be discussing, you can relate with this concept a lot. And by bias, I mean how well my model predicts training data. In variance, I am seeing how much it is doing on the test data. So what does this mean? In bias, I am seeing with my data how well it is performing, and variance, I'm measuring generalizability. So say I have low model complexity. What does this mean? That means I have high bias. I can't predict training data. So it's not at all related to the training data. So it's like very high. And the variance is low because no matter what the test data is, I'm going to perform badly because it has not captured any information about the data. When the model complexity is very high, what happens is bias becomes really low because it has captured training data to the cent%. But the variance, sorry, I have gone on to the high complexity part. So in high complexity part, you have a low bias because training data is perfectly modeled, and a high variance because even a small change from the training data will create a large error. So what we look forward to is this optimal place, which also correlates with lowering the error. And there is a derivation, there is a formula for what is bias square plus variance. But you can take it like the idea is that bias is the training error and variance is the test error, and that's your final mean square error sort of thing. So yeah, I thought that's a bit interesting. So this was the question I had asked, and a measure of the closeness to the real data, and a term we add to model characteristics of the training data. So I wanted to focus on the fact that it is on the training data, and usually to capture such information, we add this bias term also, right? So that's what I want to. But in case you missed out the word real data, training data, and you meant test bias, it's fine. I was just curious. So yeah, that was our first lecture. And in the next one, we'll see about embeddings.